So now we're going to talk about water. So when we finish the discussion of water, these are some of the questions you ought to be able to answer. What are the properties of water? What is the pH? What are buffers and what do they do? And does water have a unique role in the fitness of our environment? So first, what are the properties of water? Water basically is required for life as we know it. So it is a very important molecule. It covers about 70% of our Earth. It's a component of organisms, a major component, depending upon what the organism is. It could be composed from 70 up to 90% water, and the human body is about 78% water. It is the solvent of nature. Water does have some unusual properties. It has a high boiling point, melting point, heat of vaporization, and high surface tension. Why? What is it about water that is so unique and, at least compared to other molecules of similar size, have such high melting point, boiling point properties, so forth? Hydrogen bonding. That IMF, or intermolecular force, that is the strongest of the IMFs. So we will take a look at the hydrogen bonding of water. It is a bent molecule. If you remember your geometry from general chemistry, a bent structure is a polar molecule. So water is bent. Because it's bent, it has non-tetrahedral bond angles. It is a hydrogen bond donor and acceptor, and we will look at that closely. It has the potential to form 4 hydrogen bonds. So this is the structure of water: 2 hydrogens and an oxygen. If you also remember a discussion of polarity from Gen Chem, because this bond angle is non-tetrahedral and oxygen is more electronegative than hydrogen, we have a uneven distribution, of charge. So the oxygen has a partial negative and the hydrogen is a partial positive. This also allows it, and also keep in mind that this oxygen has 2 lone pairs of electrons, not depicted here. So it is capable of hydrogen bonding. Therefore, it can both donate and accept. So if we compare ice, or the solid form of water, and liquid water in terms of hydrogen bonds and motion, we have 4 hydrogen bonds per water molecule in ice. So this creates an open lattice structure that is very directional and straight. Water has 2.3 hydrogen bonds per water molecule. Water is fluid, so those water molecules have the ability to move around. So they are somewhat disordered compared to ice. So ice is ordered, water is disordered. We can also compare the lifetime of a hydrogen bond. So keep in mind, even though ice is rigid and more ordered than liquid water, it does have the ability to vibrate, and that does affect the hydrogen bonds. But the hydrogen bond lifetime in ice is 10 microseconds, so that's 10 to the negative 6, compared to hydrogen bond lifetime in water, which is 10 picoseconds, 10 to the negative 12. So the water, the fluid, liquid water, the water molecules are in motion, and those interactions or hydrogen bonds are breaking and reforming all the time, essentially. This is a picture of the normal structure of ice, and there are 6 water molecules involved in that open lattice structure, making, well, actually this would be a linear, all in the same plane, so to speak. And we have these layers stacking upon layers. So we have interactions with this oxygen, with the hydrogen in a layer below. If we had a depiction of a layer above, we would also see another interaction there. But this is what leads to that open lattice structure of ice. And this figure depicts the fluidity of water. And so, again, those hydrogen bonds are constantly breaking and reforming between water molecules and other water molecules. And I'm not going to go through each of these figures, but it's just hopefully to give you a visual representation of what's going on in the liquid water. So this shows the solvent properties of water. Again, it is the primary solvent in nature. And it is an excellent solvent because it is a polar molecule. It can dissolve ionic substances, salts, molecular compounds that are polar, for example, sugars, some alcohols, amines with the nitrogen atom in them, and carbonyl-containing molecules like aldehydes and ketones. This particular figure shows the solvation or the hydration of an ionic compound with water. So here this part of the sodium chloride is still in crystal form. However, as the exterior ions associate with water, they get pulled away and then surrounded by water molecules. Now, if you look at the chloride ion, for example, and keep in mind that this end of the water molecule is partially positive, this is partially negative. So these water molecules are going to orient themselves around the negative chloride ion such that they increase that plus-minus interaction. Reverse is true for the sodium ion, or let's go to this one actually. We have that partially negative oxygen and that cation, or positive sodium ion, so those water molecules are going to orient themselves to maximize that positive negative interaction. So a little more review here, perhaps. Acid-base theory. We are going to follow or review the Bronsted-Lowry acid-base theory. Definitions: a Bronsted acid is a proton donor, and every Bronsted acid has a conjugate base. A Bronsted base is a proton acceptor, and every base produces a conjugate acid, and we'll look at this again momentarily. So before we go back to looking at acid-base behavior, I also want to refresh your memory on the distinction between strong electrolytes, weak electrolytes, non-electrolytes. Well, first, an electrolyte is what? Some substance that conducts electricity in solution. A non-electrolyte does not conduct electricity in solution. So what's an example of a strong electrolyte? Ionic compounds or salts. Sodium chloride is used here. So in solution, sodium chloride, the solid, dissociates into its component ions, sodium ions and chloride ions. And it does it to completion. So you'll notice here, this arrow is in one direction. That means if the sodium chloride is dissolved in enough water, there will be no solid left. It will consist of only aqueous sodium chloride and chloride ions. Weak electrolytes do not completely dissociate. So there's less than 100% dissociation. And that's reflected by this double arrow. Here we have an alcohol, ethanol to be more specific, and this is a carboxyl group. Okay, so it is a carboxylic acid. I should have said ethanoic acid, it's not ethanol, sorry. It partially dissociates into the acetate ion and the hydrogen ion. Being an acid, it produces a proton. Okay. So this qualifies as a Bronsted-Lowry acid. Okay. It is a proton donor, or it will donate a proton. Strong acids are strong electrolytes. There are only 7 strong acids. So if you know your 7 strong acids, all the rest are weak. HCl, and they're not all listed here, by the way. Again, that one-way arrow showing that when HCl reacts with water, pure liquid water, it forms the hydronium ion and the chloride ion. Nitric acid, same thing, 100% ionization. And these are 4 of the 7 strong acids. Weak acids are weak electrolytes. We will see weak acid behavior in biological systems. Some examples given here, and again, this is telling us we've got a weak electrolyte because there's only partial, in this case, ionization. Hydrofluoric acid, HNO2, HSO4-, which is a conjugate base of H2SO4. Water is a weak electrolyte. 2 water molecules can react with one another to form the hydronium ion and the hydroxide ion. Weak bases are also weak electrolytes. This is the fluoride ion. It can react with water to reform hydrofluoric acid, and it also forms hydroxide ion. NO2- and water, same thing. Produces hydroxide, which makes it a weak base, and the original weak acid. When we have a strong acid, strong base, we can, when we measure the pH of that, or we can determine the pH of that just by the concentration of the hydrogen ion if we have the concentration of the acid. Not so with weak electrolytes. We need an acid dissociation constant or a base constant for that. So let's take a look at the ionization of water. So as we just saw, water can react with another water molecule, or as shown here, it's just shown the dissociation of the water molecule into hydrogen ion and hydroxide ion. If you remember your equilibrium expressions from Gen Chem 2, the products of that dissociation are in the numerator, and the reactant, or whatever's on the left of the equation, is in the denominator. So we have the concentration of water below the concentration of hydrogen ion and hydroxide ion. When water auto-ionizes, the hydroxide ion concentration and the hydrogen ion concentration are equal because this molecule dissociates 1 to 1. So the concentration is 10 to the -7 for each of those ions, and the concentration of pure water is 55.5 molar. So the equilibrium constant for ionization of water is 1.8 times 10 to the negative 16 molar. When we determine pH, you may remember something called the K sub W. And the K sub W equals 1.0 times 10 to the negative 14, and that is equal to the concentration of hydrogen ion times the concentration of hydroxide ion. Okay, so the K sub W, hydrogen ion concentration times hydroxide ion concentration equals 1.0 times 10 to the negative 14. So I've mentioned pH, so what is it? A gentleman from Denmark, Søren Sørensen, devised the pH scale, and the pH is then the negative logarithm of the hydrogen ion concentration. And we can calculate it with this equation. pH equals negative log base 10 concentration of hydrogen ion. If hydrogen ion concentration is 1 times 10 to the negative 7 molar, then the pH is 7. As long as we have a 1 here, and we can assume that the exponent will give us the pH. Once this number changes above or below 1, we have to use this formula or equation to calculate pH. The pKw, and I'll talk more about what this means in a bit, but it equals the pH plus the pOH, and that equals 14. So this is basically the negative, or the log of the K sub W, so to speak. If you remember, the pH scale is from 1 to 14. So if we calculate the pH and the pOH of a solution, we should have its sum up to 14. Okay, so let's consider a weak acid, and what we have here is a general weak acid, and I mentioned the dissociation or ionization constant a moment ago. And if we are going to determine hydrogen ion concentration or the equilibrium constant for that ionization or dissociation, we need to use this formula. So here is our general equation. So this is just a monoprotic acid, HA. We know it's weak. We've got double arrows here. We've got hydrogen ion concentration and the conjugate base concentration, or conjugate base produced. So the equilibrium expression, or the K sub A in this case, is hydrogen ion concentration times the anion concentration over the concentration of the weak base, or weak acid, sorry. If we have a weak base, I was jumping ahead of myself there, we would be calculating, the K sub B. We will not be dealing with K sub B's. So this is another useful equation, the Henderson-Hasselbalch equation. You need to know this equation, and you will use it constantly. And we will be doing some practice problems in a bit with respect to calculating pH using the Henderson-Hasselbalch and also another method. So for any acid, weak acid, HA, the relationships between the pKa and the concentrations existing at equilibrium and the solution pH is given by this expression. Let me first explain what the pKa is. The pKa is equal to negative log of the K sub A. So every weak acid has a unique K sub A that can be looked up in a table, in your text or online. When I assign problems from the back of your book or suggest practice problems, I would encourage you to use the pKa's or the K-sub-A's that are found in your text. If you don't and they're different, if you find a different one online, you might not get the same answer that is reflected by your textbook solution. Anyway, so pH equals the pKa plus the log, again this is base 10, of the concentration of the anion over the concentration of the weak acid. The other relationship, well, there's another relationship here, I should say, between pH and pKa. If we assume that the concentration of HA is equal to the concentration of A minus, then let's say the concentration of A minus is 1 and the concentration of HA is 1. So what does that mean? We have 1 divided by 1, and if we take the log of that, it is, I hope you know, 0. So this basically, when these concentrations are equal, this part of the relationship falls out of the equation, and the pH equals the pKa. Okay, so what are we looking at here? We are looking at what is called a titration curve. And this is describing for us the ionization of a particular molecule. Okay. In this case, we are adding equivalents of hydroxide ion, and we have this molecule which has a protonated nitrogen here, and it has lost that nitrogen when we get to this point. Okay. So we also see, so this is for this particular molecule. This is for the ammonium ion. So as you add hydroxide ion, you're increasing the pH. When you get to the point, which we're going to call the equivalence point, or the titration point, which is the mid titration, we have ammonium ion equals the ammonia, concentration of ammonium ion equals the concentration of ammonia. This occurs at the pKa then is 9.25. So that is the pH at which we reach that midpoint in our titration. That for the imidazole is 6.99, and down here we have that ethanoic acid again with a pKa of 4.6. So as we increase that hydroxide concentration, or adding equivalents of hydroxide, we are going to find that at this midpoint we've got equal concentrations of the acid and the conjugate base. At the upper point, we have completely deprotonated our acid. Excuse me. Here we're looking at a triprotic acid, phosphoric acid. So this is the titration curve for phosphoric acid. Let me take just a quick flip back here. This is a monoprotic acid. This is the only ionizable hydrogen, so we only have one pKa. However, when we have an acid like phosphoric acid, which has 3 ionizable hydrogens, we are going to have 3 pKa's associated with the titration curve. So again, on the bottom, we're increasing or adding equivalents of hydroxide ion, which again is going to increase the pH. This is the midpoint of the pK1. So here we have equal portions of H3PO4 to H2PO4 minus. continue to add hydroxide. We reach our second pK, where we have equal concentrations of H2PO4 minus with HPO4 2 minus until we get to that third pK where we've lost the third hydrogen. Excuse me, and the pK 3 here is 12.4. So when even a triprotic or diprotic acid ionizes, it is a stepwise process. These protons are not lost all at once. Now, let's introduce or remind ourselves what a buffer is. A buffer solution is going to be the combination of a weak acid or a weak base and the salt of a weak acid or a weak base. So that salt is going to basically contain the conjugate base of a weak acid or the conjugate acid of a weak base. Both must be present. Okay. So what is the definition of a buffer? A buffer solution has the ability to resist changes in pH. When you add small amounts of either an acid or a base, and we're going to do some calculations that show this property of buffers when we add acid or base. So here we have a buffer mixture. We have that ethanoic acid and we have a salt. So this is an organic salt, sodium acetate. Note that when you are writing formulas for organic salts, the cation is at the end. That's because the negative charge is on that the end of the molecule with the COO portion. Okay, so we've got a weak acid and a salt that contains its conjugate base. If we add a strong acid, maybe I should take a step back. What does this look like in solution? Being that this is a salt, it is going to dissociate 100%, so we're going to have sodium ions and acetate ions. So when we add a strong acid, which also 100% ionization, we're going to have hydrogen ions in solution, and those will react with our acetate to reform the weak acid. If we add a strong base, let's say like potassium hydroxide or sodium hydroxide, anything that contains the hydroxide ion, that will dissociate 100%, so we'll have hydroxide ions in solution, and those are going to react with the weak acid. And from that, we will get the conjugate base plus a water molecule. So the purpose of that buffer solution is to neutralize the small amounts of acid or base that may be added to that solution and